Today is a continuation of the discussion of free electron lasers, in particular SASE free electron lasers. I hope you remember what SASE means. Otherwise, I will remind you in a minute. And then there is another concept called seeded FEL, which we will not talk about it in theory now, but this you will get some hands-on experience and playing around with SASE versus seeded FEL operation while doing the tutorial, the Python simulation, which Asbjørn will then guide you through in about half an hour or so from now. And before I forget, I have updated the schedule of this course. So there is a slightly new version of the schedule for the next sessions, which will only continue in the beginning of January. In particular, the students' presentations of the different publications that students have chosen. There the dates have changed slightly, but please have a look at the updated schedule then. Okay, just a quick reminder of the formalism that we had been talking. Wait, is that actually the right presentation? I think that's not the right presentation. It should be the new one. Sorry, this one. We have seen the formulas last time. So last time then we started discussing the SASE principle to generate laser-like activity in an undulator, where the undulator represents the gain medium, just like laser medium in a conventional laser, like, I don't know, a discharge in a gas laser or optically pumped crystal in a solid state laser. Here we have the undulator that has the property of amplifying external light. If we incouple an external light beam, we have seen what the condition is. There was a resonance condition to be fulfilled. So that can be an external light beam that gets amplified, or in the SASE mode, so self amplification of spontaneous emission. There, the undulator radiation of the electron bunches that enter the undulator and start emitting undulator radiation. This undulator radiation eventually, if it's intense enough, will start to interact back with the electron bunches that have produced the radiation in the first place. And this is actually a runaway process, a self-amplifying process, which leads to what is called microbunching, so formation of this microscopic structure where basically electrons arrange themselves into thin slices spaced by half the wavelength, and exactly this self-bunching process. This is the core of SASE operation to generate free electron laser light, and exactly this we will study in a simulation in a few moments. And I mean, once this happens, this runaway amplification process, then the radiation, which initially starts out of what we can attribute this to spontaneous emission, basically stochastical emission of photons in like completely incoherent way in the beginning. These photons will then be amplified in this avalanche-like process, and the radiated power then increases across the undulator by 4 to 5 orders of magnitude in best case before reaching saturation, and then then it can stay constant or drop again, or there can be some oscillatory behavior. So this you will also see how the different experimental parameters actually control the buildup of the SASE radiation and what's happening later on. Of course, this is a great thing to produce laser-like intense radiation in the hard X-rays. So that's the main upside. Produces high peak power and actually femtosecond pulses. In contrast to synchrotrons, remember synchrotrons, the pulse duration was given by the duration of the electron bunches, so something like 10 picoseconds to 100 picoseconds. Factor 1,000 or so longer than these free electron laser pulses, so that's great. But to reach SARSA operation, we have extreme demands on the electron beam, meaning that the electrons have to be accelerated to very high energy. We need a high beam current, low emittance, also low energy spread for this to work. And the reason is that we need this very intense undulator radiation in the first place to achieve the regime of the back coupling of the undulator radiation with the electron bunches. Yeah, I mean, at intensity levels that are typically reached in synchrotrons, in these storage ring devices, the intensity of the undulator radiation is by orders of magnitude below what would be needed to have any influence on the bunch structure of the electrons. So we need this like very high intensity undulator radiation in the first place to have any chance to get into this regime of the radiation having a back action on the electron bunches. And obviously the undulator should be quite long so that there is a chance that this buildup of microbunching and amplification works over just one single pass, because we don't have a resonator. The light is not coupled back and forth many times as in a conventional laser. This all has to happen in a single pass. So obviously the undulator has to be long enough. And yeah, then okay, we have looked at these parameters before, but the main point is we need very high intensity in the order of magnitude of 10 to the 10 watts per square centimeter. And this is not in a focused beam. This is along this many meters long undulator, such that the magnetic field component of this electromagnetic wave reaches the same order of magnitude as the undulator magnetic field, which is on the order of 1 Tesla. And yeah, so getting an electromagnetic wave into the intensity level of Tesla magnetic fields is not trivial. That requires these like very strong or like, very intense and dense electron beam in the first place to generate intense undulator radiation. Yeah, and still the conversion efficiency is on the order of 5×10 to the -4 or so in terms of electron energy actually being converted into X-rays. But sounds very small number, but actually this is quite a good number compared to other ways of producing EUV and X-ray light, for example, high harmonic generation. They are typically, we are at least 2 orders of magnitude below that. Okay, now let's have a quick look at how a free electron laser is actually built, because it looks quite different compared to a synchrotron. I mean, this is all a linear arrangement, and even the starting point, the electron emission is different. It's not just some ionic emission out of a hot wire, like a glowing cathode type of electron gun, but since we want as short and as intense electron bunches right from the beginning, the best way is to start with what is called a low emittance electron gun based on a photocathode. So a photocathode is yeah, just a cathode, a metal material. So it's typically some material with low work function, so that using a UV laser that is picosecond pulsed can emit many electrons out of the surface by photoelectric effect. And then these electron bunches are directly accelerated as quickly as possible, like on short distance to as high energy as possible in order to reach like relativistic conditions on a very short acceleration range, and that is needed to prevent the electron bunches to explode, yeah, to disperse and drift apart. Because I mean, electrons are charged particles, so they mutually repel each other, and they have very light masses. So it is very hard actually to confine electrons at high density because they just Coulomb explode. But what helps is special relativity. As soon as we get them accelerated to near the speed of light, then this Coulomb repulsion or the Coulomb explosion effect is mitigated by the fact that you can regard it by special relativity and time dilation in the sense that in the rest frame of the electrons, time passes much more slowly. So yeah, the time it takes for the electron cloud to expand is reduced, and yeah, in the lab frame, the result is that a relativistic electron beam is much, we call it also stiffer. It's like relativistic stiffening effect, meaning that such a beam can remain confined to high density over a longer period of time, time enough to accelerate these electron bunches in actually a series of linear accelerator structures with some additional bunch compressing device. We will look at that in right after this. We need the electrons to be accelerated to really high energy, meaning on the order of like 10 or 8 to 18 GeV, which is typically factor 2 to 4 more than in a synchrotron. And that is just achieved by a sheer size of the linear accelerator and also by as high electric field as possible. So typically superconducting acceleration cavities are used here to really reach the highest possible electric fields in the radio frequency cavities. Then the electrons pass through very long undulators. So here we actually talk about hundreds, like 100 to 200 meter long undulators, which are actually composed of shorter sections. So because it's completely impossible to build a 200-meter long undulator in one piece. So this is composed of like 30 to 45-meter long sections typically that of course have to be very precisely aligned and mounted. And yeah, in the end we get hard X-ray or X-rays, hard X-rays up to 30 keV has been reached with high pulse energy up to 17 millijoule, I think is the highest that has been reached to date. Yeah, what is this bunch compressor? Maybe let's have a quick look at that. I mean, I tried to stress that the whole SARSA process only has a chance to work if we reach very high electron density in the first place, because we need this the high density to have high radiation power of undulator radiation to have any chance of reaching this backcoupling effect of radiation to the electrons. And for that, this bunch compressor is essential. And the way it works is that initially from the photocathode and the first acceleration stage, we get quite elongated electron bunches along the beam. I mean, still much shorter than, actually on the order of what we have in synchrotrons, like a few tens of picoseconds. And that's not short enough or not dense enough. But here we can play a trick. We can exploit the high aspect ratio of these sausages of electrons. So how could you increase the electron density? So the way it's done is that these electron bunches are sent through, it's called a magnetic chicane. This is just an arrangement of dipole magnets that basically deflect the electron bunches laterally, and the electrons are deflected on different trajectories as a function of their energy. And so this in this way, since these electron bunches are also like energy distributed in this way, we can like twist around in the phase space this distribution of electrons and turn it around such that now the electron sausage travels in this way, where we have basically the energy distribution laterally, like electrons sorted according to energy in the lateral direction, but they all come according to like at this in a very short bunch along the beam spatially or temporally. And in this way, these initial 50 ampere electron peak current bunches. So 50 ampere sounds a lot of like instantaneous current in such an electron bunch, but once these bunches are twisted in phase space, then the peak current rises to about a kiloamp, and the bunch duration along the beam now is reduced to 30 femtoseconds, roughly. And that obviously, this much higher peak current, this helps to get more intense undulator radiation emission, and that is that is instrumental for the SASA process. So just to give you a few examples, or the most important examples actually, of X-ray free electron lasers. The very first one was the flash free electron laser in Hamburg at the DESI, at the German electron synchrotron facility. And yeah, the undulator was quite long, but I mean 13.5 meters is still quite short actually for today's standards. I mean, this laser was XFEL, the operation was first demonstrated already 25 years ago now, and it was not really X-rays. It was just in the soft X-ray range, 100 nanometer, so more EUV range. But it was like the first demonstration of SASE operation for a free electron laser. And an interesting fun fact is that this whole facility, this linear accelerator and undulator, was actually not built to be a free electron laser. It was actually built as a test facility to test new accelerator technology for, at the time, like particle physics experiments. So at that time, DESI was still a particle physics institute. But yeah, then at that time also it was realized that DESI cannot compete with CERN, with the main European high energy physics institute in Switzerland. So they decided to convert both this linear accelerator into free electron laser and the ring accelerator into Petra 2 at the time. Now it's Petra 3 synchrotron radiation source. Yeah. The first actual X-ray free electron laser was LCLS at the Stanford Linear Collider facility at SLAC. And that was actually built for electron proton positron electron collisions, but also there this facility then is now fully converted into a free electron laser, so Photon Science Institute, and first lasing in angstrom wavelength range was achieved in what's the date? 2010. So 10 years later, 10 years after flash, or okay, first light actually 2009, reported then 2010. But to reach XFEL operation, the whole structure had to be 10 times longer than flash, 10 to 100 times higher electron beam energy, and also certainly higher beam current. We are talking about a peak current of 3 kiloamps here. And in that way now, already hard X-rays, 8 keV photons were demonstrated in 2009. Then, a 2-3 years later came another free electron laser online. That's the ZFEL facility in Japan, which is based on more modern accelerators that are more compact. But as far as I know, the beam properties in terms of beam energy, photon energy range is quite comparable to LCLS. Okay, rep rate is 60 Hertz, LCLS goes up to 120 Hertz, and nowadays even higher. There is another more recent free electron laser facility, which is called the PAL XFEL. In Pohang Accelerator Laboratory in South Korea, which produced first light 2016. And but again, this is a hard X-ray free electron laser, I think, with similar properties as ZFEL and LCLS. And then 2020 came the first hard X-ray laser in Europe online, and that is the European Free Electron Laser in Hamburg, which is officially not part of DESI, but it is the starting point. The electron gun is actually located on the DESI campus. You can see here this bent building on the right-hand side. This is the experimental hall of Petra 3 of the synchrotron Petra. So this is DESI campus, but then the whole free electron laser stretches a distance of 1.7 plus many hundreds meters. So I think in total 3.5 kilometers, going actually across the border from the federal state of Hamburg into Schleswig-Holstein. So the experimental hall and all the beam lines are 3.5 kilometers away. And that is a new facility, and it's a European facility, and it is the highest, the most powerful facility until today in terms of reaching very high photon energies and highest pulse energies. And this is basically all based, or it relies on just the sheer size, that it is by far the longest accelerator structure, and also extremely long undulators. And as a special feature, it uses superconducting accelerators, which have been developed at Flash before and now are successfully used at European XFEL. And a special feature is that European XFEL actually can produce bursts of femtosecond pulses with like hundreds of nanosecond spacing, up to 2,700 pulses per burst, which is great for some experiments where you need just like a high repetition rate and just many pulses in a short time to, for example, accumulate a lot of statistics. But this burst mode also causes some challenges to, if you want to do pump probe with another laser, for example, or for material science experiments where then a whole burst shines on a solid state material, then this burst mode can also be very challenging. Last, as one of the the second X-ray laser in Europe, and one of the last ones that have gone online 5 years ago now is the Swiss FEL in Switzerland. That is a more compact and cost-efficient hard X-ray laser, which it seems works very well, very reliably, just like a Swiss clock, it seems. And but the pulse energies, like the total power, definitely is lower than for these very large-scale facilities like European XFEL or LCLS in the US. So here's a short compilation of the different main properties for those FELs that are online now. With European XFEL on the top, because I mean, here we are talking about, yeah, I think reported the highest is 17 millijoule pulse energy. The design value is 100. And also, this is really an FEL going into the hard X-ray. Even 30 keV, sorry, that's the energy, that's the electron energy, 17.5 GeV. Wavelength, it's only shown in wavelengths, but yeah, this goes up to 30 keV, so extremely short sub-nanometer wavelength, some sub-angstrom wavelength. Yeah, the only comparable XFEL is LCLS in the US, but the pulse energy stays below what is reached at European XFEL. And yeah, there's SACLA, there's SwissFEL, there is Fermi in Italy, which is more an EUV and soft X-ray FEL. Yeah, here the wavelength is quite much longer, but Fermi has other very interesting advantages compared to these FELs we have been talking about. In particular, Fermi FEL is so far the only FEL that does not rely on the SARSE principle, but this is a so-called seeded FEL. And I hope we will have some time to talk about seeding in January, and also just in a minute from now when we start doing the tutorials, so you will actually already see in practice on the computer at least what seeding means and what advantages that has compared to the SARSE process. There's a few more FELs in the pipeline, or actually like LCLS2 is an upgrade of LCLS in the US, which is kind of working. So the main new feature was supposed to be that this now also uses superconducting accelerators, which should eventually provide pulses at a continuous megahertz repetition rate. But this is not achieved. They haven't achieved that yet. I think up to now, 100 kilohertz repetition rate, but continuously is possible, or alternatively megahertz pulses, but then in bursts, similar to European XFEL. And of course, China is stepping up on the scene, and there is already two FEL projects that are under construction. The hard X-ray facility Shine in Shanghai is probably coming online in 2 years from now or so. And then there is also a soft X-ray facility, XFEL. But it's hard to get much information about these facilities, because in China, as always, everything is a bit closed and not so publicly available. All right, and now we are getting prepared for the tutorial for the Python simulation, this ZFEL simulation, just to get everyone on the same page and maybe connect to this article that the simulation is based on and that you might have had a chance to look at. We had been talking about what the condition is for an external electromagnetic field to couple to this electron bunches or electrons undulating in the magnetic field. And for that, we looked at the averaged power that results from the interaction of electrons with electric field. And there was this phase here, yeah, from just calculating this scalar product and using trigonometric identities. We found these two terms where one of the two terms needed to be uh, zero, such that the time average, taking the time average of this sinusoidal function results in a non-zero time average. Yeah, because if both these phases are non-zero, then we have just a sum of two oscillating functions. If we average over time, this cancels out to zero. So one of the two at least have to be non-zero, which is called and we concentrate on the first term, the so-called secular term that should be non-zero. And that gave us the condition for, okay, time t cannot be zero, so it has this phase has to be zero. And that led us to a resonance condition. This is called the undulator resonance condition, which happens to be exactly the same formula as the undulator equation for giving us the undulator wavelength. So this means the light wavelength, in order to couple to the electrons, have to have exactly the same wavelength as the undulator light that is emitted by the same electrons. Or in other words, if now we want to get this SASE mode of operation to be active, so like a constructive or like an amplifying interaction of the undulator radiation with the electron bunches, then for sure the wavelength has to always fulfill this resonance condition. Yes, and then it depends on the actual phase, whether we have no coupling or we have net transfer of energy from electrons to light, or the reverse coupling, like net transfer of energy from the light to the to the electrons. And of course, we want the case where the electrons feed energy into the light field. So we want the middle case here, yeah, that energy from the electrons goes into the light field at the expense of the electron energy. So the electron beam will be slowed down by this process, that is clear. And yeah, we briefly discussed that this coupling of energy of the electrons into energy out from the light field into the electron bunch, which gets phase shifted, either slightly towards positive phases out of this fixed point, or towards negative phases from the fixed point. But in one case, the electrons would lose energy and go back to the fixed point. In the other case, the electrons, when they drift towards negative phases, then they would be accelerated and be pushed back to the fixed point, right? So in either case, there is this back coupling and this interplay between energy taken from the light field and then shifting the electrons away from the fixed point. So for this we can set up a what is called FEL pendulum system of equations, and exactly this. So this is a model that applies to a single electron that couples to electromagnetic field. But this can be extended then just basically by considering many particle system of n, not even single electrons, but n like bunches of or macro particles, so packets of electrons. but essentially the set of equations for this n particle system has the same structure as the pendulum equation, in the sense that we have derivative of a phase that relates to eta, and eta is, you can see here the definition of eta. It's the deviation of the energy. Gamma is the relativistic Lorentz factor, which is proportional to energy, and its deviation from the resonance value, normalized or in relative terms and normalized to FEL parameter. So this is essentially the you can say the energy eta, and theta is the phase shift of the electron oscillation with respect to the fixed point where the electrons would not experience any force. And that's one equation, and here's a second equation, which again couples deviation of the energy, the eta, to, in this case, okay, here it's sine phi. Here this is just cosine phi. But yeah, so it has the same structure. I tried to like really relate the two models with one another. So essentially, we have the phase just defined in the same way as the phase phi in our previous derivation. Eta is this energy difference. In this case, A is a complex radiation field amplitude, and instead of using time, we rescale, or yes, Kc is omega times time. This is like omega t. We rescale this to a scaled longitudinal coordinate, just so that you, if you want to look up the definitions of these variables that will show up in the simulation. Okay, that's it as a preparation, like just for you to get an idea if you haven't had the chance to read the paper. The model essentially is an extension of this one electron FEL pendulum model, just to n particles, where it's not just n electrons, but n like packets of electrons. I think it's to just increase the charge and increase the interaction strength. But essentially, it's just a many particle extension of this undulator, of this FEL pendulum model. All right, then that's what I wanted to say. Now I think it's time to actually start with the simulation, and so Asbjørn will take over, and you should hopefully be prepared to switch on your Jupyter Lab, Python, and then get started.
Yes. So yeah, the way that this yeah, we uploaded this folder yesterday, right? And the way it's set up is basically that you have a there's this example, which is just like a little framework for running different parts of for running the simulation up here, and then I tried making some quick functions to help plot parts of this output, which should hopefully make it simple to get started and play around with. There's a couple of things because when I was playing around with it yesterday, I kind of did it all in one big file here in this. Playing around with it also earlier than this, but I would before you get started, just set this E spread to 0, and also let me see. Yeah, there's a random seed So this guy you can set to 0 set steps. I'll set this to 200. E-spread I would set to 0, and the beginning just set the random seed to number, like 31, for example. Yes, and then for there's some things you can try here in exercises. Some small things to play around with. I would maybe move this up here. Just if you are gonna try this shot-to-shot variation, try it before the seeded, because the seeded mode it cheats a little bit, but anyways, this is not a yeah. I think we were planning to maybe do like breakout rooms, possibly.
Ah, yes, exactly. Maybe that's a good idea.
And
Tanuf,
then
do you
you
think?
can, yeah,
Yeah,
try it on 2-on-2 or 3-on-3 or something like this.
good
So
idea.
could you just repeat? I didn't hear.
Is it possible to create a few breakout rooms and distribute participants maybe in groups of 2 or 3? I mean, how many are
Sure,
we?
Professor.
Sorry?
I think, sure, Professor, we can do that. I think, but
Maybe,
Jayesh would have to
I
do
guess
it, I guess.
3 rooms should possibly be enough already, because it's not so many.
Sure, Professor.
Yeah, and then
Jayesh, I think we can only make the break.
so in this one room where I was, there weren't too many Am I in a breakout room or am I?
We can also just close all rooms.
Yeah. Can you do that?
Yeah.
Yeah. Then do that.
Recording is progress.
Okay. Yeah.
You can talk.
So I guess
yes,
it maybe this getting this Python to work was a bit yeah, short notice given how late I sent out the uploaded this thing, and now we're still waiting for some people to come back from the breakout rooms, it seems like, possibly. Yes. So yeah, I mean, we can also just do it in a way where I can share my screen, and then we can run this in a couple of different ways. You can, of course, have it running yourself and play along at home if you also want to. But yeah, if not everybody has gotten Python to work, then possibly, yeah. So does that sound good to everyone?
Yeah. Yeah.
I think it's
Yeah.
that's
Yeah,
new,
that
and
could
then
work back.
people have enough time to play around by themselves.
So
And we could maybe we could have another session in January to pick this up and see if anybody has learned more or found out things. But for now, I think to get started anyway, it's a good idea to see
sure, yeah.
what can be done.
So yeah, as noted before, this is basically the little framework for running this program. I ended up you can. I think I suggested it's the first time you can just install the ZFEL, but I ended up just taking all the scripts and pulling them out, because then you can go in and like check that. Yeah, I wanted to check some things basically. Anyways, so yeah, there's some things to play around with here. The first simple thing is we have this params calc, and basically you take this input and then it gives you out a lot of parameters.
Could you just quickly say what the main input parameters are?
Yes, sure.
Which
yeah.
parameters it's worth changing?
So I tried putting a little note about it here, but very shortly, we have this n part. So there's like again, this is this microparticles. It doesn't make sense to simulate every electron, but we want to simulate enough electron-like things that that you have something that behaves like a bunch of electrons. This you can change. So if you want to make your simulation longer, you can double it, or you can go down. I think the simulation does some splitting up of these. So like if you go below 120, it'll start complaining, and they should be divisible by 4. But then there's these S steps and Z steps. The way the solution works is that we are stepping along the bunch in steps of there's like 200 steps along the bunch, and then we step along the undulator also. So you can imagine that you start at the back of the bunch, and then you walk up, and then any light that's generated back here will be relevant for stuff that happens further up, but stuff that happens further up is not relevant for the electron down here. So this way we can start from the back, and then you move the electron bunch forward a little bit, and then you have your next part of the undulator, and then you repeat the process. that's these two numbers. If you are playing with the undulator length, it may make sense to change the amount of steps along the undulator, just so we're not walking, taking big steps, because this is, of course, it's a differential equation. So if you've seen these pictures of how you can, if you have too long steps, you can sort of diverge away from the expected path. That's also the case here. There's this energy here. This is the electron energy. So yeah, it's pretty self-explanatory, I hope, that how much speed do your electrons have?
In EV, right?
EV, yes. Yeah. And you can go in and completely mess up your lacing by putting an E spread on here. So if the electron bunch is not all moving at the same speed, then actually let me. So right now it's just a simple SASE. And this takes like 10, 20 seconds on my computer, but this depends, of course, on these three. So this is the power output. But yeah, if we go and set the energy spread to, okay, this is 10%, this is possibly quite high, let's say 1%. So there's 1% difference in the electron energies.
Okay, so even a few percent energy spread already has a big impact.
Yeah, basically, you can see that we are starting to to get out, but before the power was 14 gigawatts, 15 gigawatts or something at the highest. Now it's maybe, what is this, like 800 watts, 800 kilowatts.
Okay, so not even really, it hasn't really even started lasing.
Yeah, so this is this E spread. So basically how much difference do your particles have in energy. There's these two, emit N and beta. These are basically used to calculate the divergence of your beam. So it's a very cheap way to get a higher number in the simulation, is just to assume that your electrons are tighter, tightly focused. Oh, okay, actually, I could have sworn this was a linear thing. This looks very similar to before.
I mean, I don't. Okay, beta, I'm not sure exactly what it is, but the emittance for sure should be nonlinear, because like quadratic, I would say, because I mean emittance is probably in X and Y, like
Yes.
divergence in X and Y directions. So lower emittance means quadratically more narrow beam. And also of course, the beam density enters maybe in a nonlinear way. I'm not sure.
So numerically in the simulation, the thing they do is that when you then do this params calculation, then they together give you this sigma. I guess this is chi-squared possibly, or x-squared, but it's just the final divergence. Yeah. There's the current. So how many electrons at peak of your bunch do you have? And we have the undulator. These are basically the electron bunch parameters. And then you have some undulator parameters. You can set the period. So if you want, see here, this is with 3 centimeter periods, we get a wavelength in 800-ish EV. We go down to 0.1. This
1 centimeter.
1 centimeter, yeah.
We
should get something.
Get shorter wavelengths.
So
Yeah.
here we are up in 25. And then you can set the undulator parameter, this undulator parameter. So this is this this value here, the magnetic strength of the magnetic field divided by the undulator wavelength, and this is the thing that's adjustable on most of these by playing around with how tight your undulator is. So I think we are now down. We are back down to we're back down to 0.3, but this went from 3.5 to 2, and we lost a lot of power. But now the pulse, the photon energy is much higher.
Okay, 2 kV roughly.
Yeah. And then you can set the undulator length. Because this is a simulation, it's quite easy to stop along a certain point, right? And say, okay, what's like, we can also store the value at 45 meters or 55 and so weiter, but this is the total length that we are integrating over. I am not entirely sure what this does. The radiant wavelength. This does something to calculate the this is used in some data parameters. Okay, yes, this is this T01 parameter. So, but what exactly it represents in the undulator, I am a little uncertain of.
Maybe that's for the seeded mode.
Could be the seeded mode, yeah. So, but this is the quick overview of. Oh yeah, and then here you can set the seed. You can, if you have a seed, then basically the electron positions are slightly randomized in the beginning. If you have a seed, they are always randomized to the same position, so you get the same output curve. If you don't have a seed, they are random from shot to shot.
But I mean, in the seed mode, then also it adds this additional low electromagnetic wave, right?
Yes. Okay. So there's two seeds. This is the random seed is the seed that is the. This is just used to set the random generator.
Okay.
And then
seed for
separately, a free electron laser has a seeded mode, which
Okay, sorry.
No, but it's a bit confusing because they are two different things named the same because the seed here is a computer science term, and here it's a So this is the last bit here is that you can change from SASE, the spontaneous amplification of self-amplification through spontaneous emission, to the seeded mode. So actually, let me just go quickly back here.
Yeah. I had a doubt.
Yeah, sorry?
I had a doubt actually. So what exactly is Z and S step?
What is the next step?
What exactly is the Z and S step?
So this is so it's this the way this differential equation is solved, all of these differential equations are solved, is that we start at the back of the electron bunch, and then we step over the electron bunch, and then we move it a little bit forward, and then we step over it again, and this gives you the field as it evolves up through the electron bunch and up through the undulator. And first stepping through the electron bunch is the coordinate S, And then when we move it forward to the next undulator step, which is the coordinate set.
Okay.
So
Yeah, got it.
That step is the increment.
yeah, so it not increment, but we have 200 steps along this distance of 70 meters.
Yeah.
So you can see on this plotting, I'm plotting the power in two different ways here from this output. Power set is this curve, and this gives you basically what is the power of the light, or the lasing at a specific point along set. And power S gives you this thing on the right here. So this is this curve, but for every part of the bunch, basically.
If I'm not wrong, like S moves along the bunch and Z is basically the bunch moving over the undulator plane.
Yeah,
Okay, thanks.
exactly. Yeah. So I think in some of these plots, when you look at the manual for this ZFEL, it also like they will talk about Z kind of as the time parameter, which is weird because it's of course in meters, but if you think about it as the bunch moving forward through the undulator, then it kind of makes sense that it's the time parameter because you're at different steps or you're at different positions. Yeah.
Can you show again this? But then also this 2D plot, like power in this density representation with S on the y-axis and Z on the x-axis. The fact that we see these like along the vertical direction, we see these strong modulations. This means that not the whole electron bunch emits radiation like homogeneously or uniformly, but within a bunch you have these smaller sections where lasing starts, right? And where the microbunching occurs, and then those amplify the light very intensely. But then you have also like dark regions within the electron bunch where just the SARSA process has not started yet, and probably actually electrons are then depleted out of these regions possibly. But I mean, this is very characteristic for SARSA operation, that you don't get one nice homogeneous pulse emitted from the bunch, but every bunch produces a very spiky spectrum of light pulses. And this occurs in a very random manner because lasing starts out of the shot noise, essentially. It's spontaneous emission that triggers the lasing. So for every bunch and like every laser shot, the spectrum, so this spike distribution of light emission looks different. And we will maybe talk about this in January also. That's a severe drawback of the SARSA process, that because there is no resonator that feeds back the light and like really produces this very monochromatic, well-defined laser mode, but the field profile emitted from the bunches in the SARSA mode has this very spiky, noisy spectrum because it directly is born out of the noise, so to say. Then we get very strong pulse-to-pulse fluctuations in both the time structure, like this peak structure in every pulse, and also the spectrum. Can we see the?
Yeah.
Yeah. Okay. I mean, here this one looks more or less like a homogeneous or like a uniform spectrum, but still we can see that within, like in the vertical direction, we have the energy distribution.
Yeah.
So also spectrally, these SARSA pulses have a very pronounced peak structure. And this also the spectrum of every pulse looks different from shot to shot. So if we are thinking of doing some spectroscopy to basically probe a very narrow absorption line in a molecule or atom or so, then it will be very hard to do precision spectroscopy with these SARSA pulses because yeah, because of this very spiky, noisy spectrum. So that is like a fundamental drawback or a complication in the SASE mode. So, and that's like that people are working on trying to improve this. For example, by doing the seeding, like operating an FEL in a seeded mode improves these things a lot. But I mean, yeah, I guess you will show an example for seeding also.
I do actually have some. So I did a little symbol. So what if you want to see the shot-to-shot variation? A very simple way is just to go here and set this random seed to none. Then you get this thing where it's not the same shot every time. And then either you have to run it a bunch of times or you do thing that computers are good at, which is just tell it to do the same thing a bunch of times. So here I have a little, this is no seed. We are in the SASE mode and it's the same parameters as before. And if you run this simulation 10 times and plot the power and the spectrum, you get something that looks like this.
Okay, nice shot to shot.
So yeah, so you can see the saturation. This L set is about the same. Like it always takes about 30 meters for us to reach sort of the lacing plateau, but then some of them drop quite a bit down, and some of them, yeah, they all develop slightly differently. And similarly for the spectrum, like if you were hoping that you have some resonance at 820 that you want to look at, then this shot will be completely useless, while this shot will be fine. And yeah. So I mean, there's still a lot of power in these, but these are still logarithmic, but just to show that it's not really the same thing.
And these are the spectra at the end of, like, at the Vmax,
Yes,
right?
yes. So this is the this spectrum, and then I'm just taking the last slice, basically.
Is it like what would be more realistic would be to take slices, let's say, close to the saturation, the first saturation point, because this is what you would usually want to operate a FEL, but you want to get the full buildup of power, but then stop stop the lasing at that point to avoid this strange oscillations, and which will probably actually spread out the bunches even more. And so typically you want to have full buildup, but then just cut off at the highest point to get the shortest pulses, the cleanest spectrum. But yeah, it would be nice to see the spectrum there. Is it possible?
Yeah, this would be about 80, I think, then. We are 35, so 35 would be 100. 30 becomes, yeah, let's try 85 then.
85 is what?
This is the 85th index along
okay.
the set coordinate. Oh, shoot. Forgetting to change my... Okay, there we are. Should be... Yeah, this run takes a little bit of time because it was 8 seconds for one, so now we're doing 10, so... Yeah.
Yeah, 80 seconds take a long wait for them.
Yeah, okay. One thing we can look at in the meantime is we were talking about this seated mode, and yeah, this is maybe simpler to show here, but you can try seated mode if you go down here to I opt. So I shouldn't point. You can't see my finger. I opt to change that from SASE to seated, and then
you can run 2 instances at the same point at the same time.
it should be okay because I think all of this Python code is just like normal Python, so it's single threaded and each thing runs on one computer. Yeah, so then you get something like the power suddenly looks like very nice and even, right? There's lacing throughout the entire bunch, and then the pulse slips a little bit forward. Then there's lacing through most of the bunch, and when you go to the spectrum, it's also like looks much sharper. Not as
in particular at earlier times it would be much sharper, right? There we can actually see that when we go beyond this saturation point, then the spectrum starts broadening.
Yeah.
Because once the electrons have basically converted all their energy into the light field, but you keep pushing the electrons through the undulator, and you still have this back coupling of electrons and light field, then like this nicely micro bunched electrons would start spreading out again. And that of course deteriorates both the spectrum and the time structure of the pulses. So that's why you want to stay ideally on this very first peak after the first build up and stop it there.
So okay. This is the
But still we have propagated up to 70, or no? This is only the...
So now this is the spectrum at the 85th part of the spectrum, which we can let's get the computer to do this. So okay, that's pretty good calculation if I do say so myself. So we're at about 30 meters. Yeah. And okay, they are not as different from each other, but they're still these are not the same curves.
Yeah, but they look really more similar, and also probably they're overall narrower than the later spectra, right? Yeah.
Yeah. So one thing, and the reason I mentioned that.
Sorry, can we do the same thing here within the seeded mode? Also going to just 30 meters.
Yeah, sure.
Because then the peak should be really sharp, I guess. Okay, maybe it's a little bit longer, further than 30. Should be 35 there.
Yes. So 100. Yeah.
Okay, yeah, there now you see the seeded mode. Now the spectrum in the optimal, say, outcoupling point really is extremely sharp. So this is a laser-like spectrum now.
Yeah. So one thing I think as I quickly mentioned earlier is they cheat a little bit because you might notice that when we run here in seeded mode, this is the same seed, and then in seeded and in unseeded, the saturation point is after the SASE saturation point, and this is of course this wouldn't happen in a real free electron laser, because if you are seeding, then you'd still have the possibility of spontaneous emission. But this happens here in the simulation because when we run in seeded mode, this you can see if you go to the particles here. Then they generate in seeded mode. They generate the, so you see here it says the way it works is we start over in this SASE 1D. This does a lot of stuff, calculates some parameters, and then it calls this general load bucket. General load bucket, if the particle position is none, calls the load bucket. And this load bucket is what gives us our etas and thetas, these phases and energies that we then can propagate. But if this load bucket is in seeded mode, then we cut out some random noise that shows up in the SASE mode. So this bunch is unrealistically orderly compared to a real life bunch, because you of course you can remove the SASE component of but this is this is a simulation, and
You can do everything you want.
exactly, yes. So, but you might also notice if this worked last time, if you set the seed power to 0, this again, right? We don't get anything because there's nothing to self-amplify, because there's no randomness, and we need a little bit of randomness to start this self-amplification process. So yeah, this is that's
Mainly it, right?
yeah, it's more or less it. I don't know if time-wise we
are done in principle.
Okay.
I would say. I mean, we can ask, is there any questions, or I mean, has anybody tried playing around and got stuck with not getting any lasing to work, or did anybody find out something interesting that he or she would like to share? I mean, for sure, you should play around a little bit over the next 2 weeks or so. We could have another session in the beginning of January to wrap up on this. And by then, hopefully, you will have the chance to have played around a bit for yourself and try to like get some understanding out of it. I mean, definitely we will pick up on this topic of seeding, like what exactly seeding in FEL means, because this is a very interesting new type of new mode of making a free electron laser lace, which obviously, as you have seen, has the benefit of controlling the output spectrum, but also the output pulse shape much better than the SASE mode. So there's various attempts and various techniques to try to implement this kind of the seeding. So we will talk about this in January a little bit more, but please keep playing around and try to see how the different parameters influence how the FEL, this SASE or seeded mode works. That's very instructive. I mean, any questions? Or I guess if somebody got stuck with not being able to actually run the whole thing for one reason or another, then I mean, Asbjørn, maybe you would be ready to answer questions or help out with,
of course,
getting this to run.
I think if you want to send me an email or something, that should also be, I don't know, I think my email is in the email list, but I can send an email around so people know who to write to if they have some, like I'll happily help set it up. Yeah.
Okay. If no questions, no comments, then I would say we call it a day and wish you a good night and many nice dreams of free electron lasers generating perfect pulses.
Thank you.
And then we please have a look at the updated schedule for then the next sessions that will resume in the beginning of January.
Okay. Can I know how to save the data, simulated data in Word or any file?
So do you want to save these figures that
Yeah,
it generates?
figures and analysis parameters along the figure.
Yeah. So and the simplest way to, if you have like a figure like this,
Yeah.
is that so you want to like have a handle for this figure, and then if you call figure dot save,
Okay.
I think it is, then you give it a name. So this is my power,
Yeah. Any name.
whatever, and then run this.
Okay.
Then it automatically like generates you a little. So by default it's a PNG, but it's quite versatile. Like you can do PDFs if you want to put it into a publication and stuff like this.
Okay.
If you have a lot of numbers, then the simplest is to do like numpy.save underscore txt. Will just
Okay.
give you like a long list. But it depends a little bit on what thing you are using in Python. So I'm very happy with, if you want to do something like more structured, there's a module called pandas, which is really good at like right, NumPy does arrays. There's nothing, there's no information on the coordinates about what each coordinate means and stuff like that. Pandas does what they call data frames, which have like, okay, this column contains energies, this column contains whatever. And Pandas has a very broad suite of save tools. But again, if you just want to save a figure, then I hope that explained it.
Yeah. I understood that.
Right, super.
Okay. Thank you.
Yeah.
Thank you so much.
Okay, then good night and see you again in January. And don't hesitate to contact either me or Esbjørn if you have any questions regarding the course or regarding the Python specific things.
Okay.
Bye-bye.
Thank you, sir. Bye-bye. Good night. Thank you, sir.
Thank you. Thank you, sir.